charges 6 through 10. Okay, so we got two charges located. Okay, this one is really more of a thought question, which is why it's a quicker multiple choice. So we know that the voltage is going to be zero infinitely far away. Okay, we also know that the voltage is going to be balanced like right there. Okay, and here's why. Um, this is double the charge, and so you're going to have to be double the distance away from it so the voltage is balanced. Now remember, voltage is kq over r. Remember, just r, not r squared. So if you want this voltage and this voltage to balance, you got to be twice as far away. So this has to be broken into a 2-to-1 ratio. It means you're 2/3 of the way here. So how far are you away from the origin? Well then, 5/3 of D. What's the radial component electric field associated with the potential? Okay, now remember, this is something we have to know, right? Well, if we know the integral, then we also have to know that the electric field is the rate of change of the voltage, and it's negative for the same reason the negative is in the other one. And so all we have to do is just take the negative derivative of this. Just be careful that you get a negative from the power rule, and you also get a negative from the actual relationship between field and voltage. So we get that guy. All right, in the region, the electric field is proportional to, okay, this is really just a Gauss's law question. And proportional to means just we don't care about K. So just get rid of the K. All right, we're looking for R. We're looking in the region between R1 and R2. So we're looking in this region. So if your Gaussian surface is in there, well, if you're inside here, right, if you're in there, we don't care about Q2 at all. The only electric field that you're getting is from Q1. And once you're outside, in this region, electric potential is relative to infinity. Okay, so in there, we do get both because they're scalars. Right, you're adding them both up. It's relative to both of them, right? We're pretending like both of them are at the origin, and so in this region, it's just proportional to KQ1 over R and Q2 over R. It's just like their point charges for the voltages. All right, so a battery's connected, which is found. Oh, this is really not that much of this unit question talking about batteries, but this is like a capacitor and this is a battery. And so if you want to produce this, eventually we'll decide that batteries in series add their voltages. So adding a battery and a battery is like a TV battery, when I say like a remote control. So if you look at lots of things, or even your like graphing calculator, they'll take batteries and they'll put them in series. So like two 2-volt batteries in series are really like a 4-volt difference. And they are aligned properly. So it's like plus minus, and so we go this way, which means this side is going to be at a higher voltage than this side, and it's a 4-volt difference here. And again, it doesn't matter whether it's -2 and +2, it matters that the difference here is 4, just like this. But don't worry about this question. Nothing like this will be on this particular test. Okay, back up to there. The force on an electron on the 0-volt line. Okay, so the 0-volt line, we know that the electric field is going to go this way, going left. And so the force on an electron is directed to the right. If we don't know this is spaced exactly, then we actually don't know what the actual magnitude of the electric field is, because V equals ED. If we knew that distance, then we could find the electric field, and then we could actually find the magnitude of the force on it. Again, it's an electron, which is why it's going to go right. It's going to go towards a higher voltage up the electric field. Okay, the potential on ASA. All right, this one is hard. When you get a charge on something and you keep adding more charge and adding more charge, think about if it's only got like a +1 and you want to add another +1 to it, it's kind of hard, right? But then once it gets up to like +5 and +6 and you keep wanting to add another charge to it, it gets more and more difficult because you're taking a +1 and you're trying to put it on a +6. It really doesn't want even more positive charge. And so the work really is going to be this accumulation of this, where the charge keeps growing. So you're going to integrate from 0 and you're going to accumulate all these little bitty dq's from 0 to all the way till you get to capital Q. And we know that the work done is the voltage, KQ over R, times this dq. Again, the voltage is not going to be constant because you keep increasing the charge, which keeps increasing the voltage. So it's pretty complicated. This is not asking you to do it, it's just asking you how you would set it up. And so really you're thinking about the calculus version of this. So you're integrating dq of the voltages. So hopefully C makes sense after you thought that through. Other than infinity, electric field is 0 at the point. Okay, somewhere over here, right? You're going to have to be closer to the +2 to make its electric field equal to the stronger charge. So you got to be further from the stronger charge, closer to the smaller charge. And in there, the field is going to be, pushing to the right and then also pushing to the left, which will cancel. The electric potential is negative. Yeah, never. I mean, both the charges are positive. So how are you going to add up two different KQ over R's when they're both positive and end up with a negative? So that's not going to happen. All right, the force. The biggest the force is the biggest the E field. And the biggest E field is when there's a biggest change in voltage, which is slope. Again, when voltage is constant, that must mean there's no electric field. When voltage changes, there's a big electric field. And so in this region right here, the voltage is changing the most, which means that the electric field is the biggest right there, which means that's where the particle would get the biggest force. Force is related to field. Field is related to the change in voltage. Okay, so we're just going to take this millicharge and 2 millicoulombs, and we're going to make it, that distance doesn't matter, and we're just going to, the work is 5 joules. So if we know if the work is 5 joules and we know we took a certain charge, then we can figure out what the voltage difference must have been to do that, right? We're just doing the work equals QV, right? The increase in potential energy is just the amount of charge times that voltage. Okay, this one is pretty intense. It's intense because it's got everything, done here. So we have a proton there, and then we have this electron orbiting it, okay? And so what is making it happen? Well, we know that the force is the force of attraction here is KQ over R squared, right? That's me doing this. We know that to be true, okay? And so that's what's actually making this go in. It's like gravity. And so the force equals mv squared over R. And really, you're just multiplying the R over and getting mv squared. And then you're going to multiply both sides by half. And then the K really is a 1 over 4 pi, which is where the 8 comes in. The two charges, are really just the charge of an electron. Remember, an electron and a proton have the same charge, just one's positive and one's negative. So that little E is just the two charges. And so really it's circular motion. We know in circular motion, we can replace acceleration by v squared over r. We know that the force attracting this, meaning we know the force making the electron go in a circle, is just Coulomb's law, KQQ over R, and that's this, KQQ over R squared, and that equals mv squared over R, so then you multiply by R, and then you get it. I also make a point that energy. This is the only thing that even looks like an energy. Actually, sorry. These two have to be one of the answers because, it's energy, right? We know energy. The formula for energy is a KQQ over R. This is just one charge. This is two R's in the denominator, and this is 2 powers of R in the denominator. And these are not energies. They don't even have the right dimensions, meaning they don't have the right units. Only B and C make sense, and since kinetic energy has to be positive, well then actually you can just circle B and move on. You don't even have to do anything. 71. Okay, so we get an electron, and we know it's going to go through 2 large parallel plates. So the energy it gains, the work done, is just going to be QV, which is this, And the work done is going to make it so it's equal to kinetic energy, right? The E, again, that's just the charge on the electron. So instead of a Q, I just put an E there. And so if you solved, you could say that the velocity is proportional to the square root of the voltage, which is what this is saying. Again, you're just basically saying how are V voltage and V velocity related. Voltage related to velocity squared, so that means that velocity is related to the square root of voltage. Okay. Okay, this is the graph of electric potential inside this conductor, right? Inside the conductor, no E field, so a constant voltage, and then the voltage falls off like 1 over R. The electric E field, okay, so E field needs to be 0, and then falls off like 1 over R squared. Okay, this just doesn't fall off fast enough. Remember, E field is 0 inside a conductor, and then outside it's like a point charge, so it falls off like 1 over R squared. This wouldn't be a terrible answer. It just doesn't fall off fast enough, right? This only went down half when you double the distance, and we know that's not what a 1 over R squared looks like. E field at the center. Remember, it's a vector. So in this center here, all the electric fields are going to cancel because they're symmetrically around that guy. Now, the work done to take a charge, so you get a charge way over here, and we take that charge and we slap it in there, right? It's going to be each one of those little Q's. Well, actually, let's do it this way. Let's think about it in a voltage. In a voltage, don't we know that the voltage would be K, Q over R? And since there's 6 of them, the voltage there would just be 6 KQ over R. Well, if you have 6 KQ over R voltage and then you want to make another charge on there, boom, there's the work done, which is the answer. And this whole stupid 2 pi epsilon naught, it's just taking the 6 and the 4 and making it 3/2, which makes it look confusing, but they just reduce fractions to complicate it for you. All right, here are some equipotential lines. So we know that the electric field is always perpendicular to this. So if you think about it, like the E field is going to go like this and then like this. Oh, that's not going to be good. The thing's not working very well, but hopefully you see that the electric field essentially is going like left and up. Always perpendicular. Now the electric field like right there is straight, right? Right there is basically straight down. And electric field at C is pretty much straight up. Electric field at D is like that direction. B is that way, right? Always down voltage and perpendicular. So at A, it's kind of going to go perpendicular to A, so it's going to go that way, which is why that's right. Which electric field is the greatest in magnitude, right? At B, look how dense these field lines are, right? The voltage changes really quickly over a really small distance, which means electric field must be really big. All right, how much work must be done to take that charge from C to E? C to E is 10 volts to 20 volts. So it's a 10 volt increase, and I'm taking a charge. So it's just Q times V. So it's just -1 times 10, and you just get -10. And again, this is micro and that's micro, so you don't have to do anything with that. Okay. A solid sphere has charge distributed. Okay, so once you know that it's the charge is distributed uniform, it can't be made of metal, because if it was made of metal, it would be a conductor. If it was a conductor, charge would be spread over the surface of it. Okay, so going back to the derivative, right? The electric field is the rate at which the voltage is changing, so we take the negative derivative of that. And again, since it said the word magnitude, we don't actually care about the negative anymore. We just take the derivative. All right, what is the direction of electric field? Okay, so if you think about this, doesn't this look like the voltage is growing as you move away? So what happens to the electric field? It's got to point in. Electric field goes from high voltage to low voltage. So we know that the voltage over here is going to be a big voltage, and the voltage at the center is 0. So the electric field has to point that way, towards the origin. A positive electric charge is moved at constant speed between 2 locations with no work done Okay, if there's no work done, must be moving on an equipotential line. There's no work required to move along an equipotential line because you're just staying at the same voltage. What is going on here? Okay. A non-connecting house here carries charge, shoots, oh, so we're here. So we're looking at the voltage, right? So the voltage here, it's all about the voltage change, right? The work done is going to be the charge times the change in voltage. The voltage here is going to be KQ over little r, and the voltage here is just going to be KQ over capital R. Well, the work done is Q times that voltage. So we get Q, that little Q right there, and the other one is KQ over R minus another KQ over R, just the change in voltage. Here's the voltage on the surface, here's the voltage on the perimeter. That difference, which is the subtraction, and then multiply by the charge you're taking is then the work done. Okay, and this last one, this one we don't have to worry about because it's actually talking about the energy stored in a capacitor. Forget it, don't need to know it. But this one, the potential difference, and again, they're giving you electric field as some function. So E equals AX plus B, so it's really like E equals 40x plus 4, and all we have to do is integrate that. Right, we're gonna figure out the potential difference. The definition is the negative integral from 0 to 0.5, integrating ax squared plus b is just ax plus b is ax squared over 2 plus bx, and then evaluate from 0 to -5 with a negative, and you get that -7, which is the potential difference between those two locations. So there's a drop of 7 volts going from 0 to 0.5. Right, so that's really just doing a definite integral using our definition for voltage. Okay, hopefully these two videos together, kind of sum up all the stuff we looked at in the potential energy and electric potential, which means voltage, multiple choice questions.